Time to go again. Yeah? So I just wanted to quickly repeat some things that we talked about last time before going ahead and address one or two questions that came up with various people in conversations. Okay, so we started off by describing stress. This object is the force per area in the j direction on a plane whose normal is in the I direction. We looked at that for a while. We looked at force balance. And I wanted to remind you what this object is. If you have a piece of material, this is the force experienced by that piece of material due to neighboring pieces of material, all short-range forces. Everything communicated through the wall of the sample. Okay? This is the other way of accessing that piece of material directly. This is some long-range field, gravity, or you turn on a magnetic field or whatever you like. Okay, so these are body forces. And this is the equation of static equilibrium. We also, or at least I waved my hands a little bit and asked you to look at torque balance on a volume element. And if you look at torque balance, you'll see that this tensor is symmetric. Sigma ij is a symmetric tensor. We talked a little bit about what the diagonal version of that tensor looks like. We said that the diagonal version would have principal stresses. We talked about how the diagonal version of the tensor will also tell you something about the pressure. Okay? And we said that something that had only hydrostatic pressure would never have shear components. But as we discussed in the afternoon for those who are here and in the problem I talked about a little bit, you can have unequal diagonal elements and you can generate off-diagonal stresses in other directions. Then we talked a little bit about strain. And you remember where this came from. The interpretation of strain comes from changes in distances between material points. Okay? So we came at it by looking at how two material points separate in space. And we showed that okay, where this is that object, told how material points separated from each other under a displacement field u. Okay, so if everything moved by u, this takes out all rigid body motions and leaves you with what's left. In many texts and in many contexts, you reduce to this. That's okay, but it's not okay for what we will do. For most classic civil engineering contexts, this piece is okay. Okay? But this piece is necessary for what we'll do today, and you'll see this thing showing up once in a while. But I'd like to ask you to go check. This object all by itself is not even rotationally invariant. Take a block of material and just spin it through 90 degrees and see whether you get a strain-free state. And you'll find you won't. Okay? So it's actually, there's something nice about it. There's some components of strain that are involved in canceling other components of strain. Okay? So we're going to, for the most part, work with a lot of this, discarding things as appropriate. The next thing we talked about was Hooke's law, which was a relationship between stress and strain. So the one that's easily written on the board, of course, is this one. And then I forget always which goes where. And then I have to go several pages back. To remind myself which goes where. Help someone? Someone who's quicker with... And I have to read upside down. Thank you. Okay. Then we also wrote the maybe more intuitive but clunkier version with the Poisson ratio and Young's modulus. Okay. And these are completely equivalent, and probably I will use more of this, and I wrote this because it's easy to write. So one small comment I wanted to make is that I won't do it in painful detail, but because we don't need to particularly, but you can see the following, right? I have here displacements. So if I'm trying to solve the problem that I normally do in kinematics, I take an object, I take initial conditions, I send it flying somewhere, I want to know what happens in the future. My program here would be take the displacement field. Okay? It's given in the stress tensor, so take this. Okay? Put 1 into 2. Let's call this 2. Okay? So I'm going to get sigma as a function of u's over here. Yes? And then I will take that and put it in the badly numbered 3. Okay? Put that in 3, and then I'll have a differential equation just in u. Okay? Shall I do it? I'll just write it in the notes. But you see what I'm doing? I have something that's just a function of u. I'm going to express stress in terms of u. Okay? So right-hand side will only be in terms of u. Then I'll put all of that inside here. And this will be an equation only in u. Okay? Then you can say, well, if the forces are such and such, then these will be the displacements if you solve that differential equation. Okay? And in fact, you can also add dynamics if you want. You can put on the right-hand side, I've put F, you can put MA. You can put rho second derivative of U. Okay? That's the way you would go if you wanted to solve, for example, for elastic waves. Okay? You can get all kinds of, all the wave phenomena you want in elasticity out of that. Okay? Not going to do that. The next thing we talked about was this, but I wanted to hold on 1 minute and tell a little bit more over here. There was some question about what is linear and what is not linear. Everything about the stress-strain relationship will be linear in what we'll do. Okay? That's to say, if I'm plotting a graph of, forces against, and stresses against strains, these will all be linear functions. And we're going to work in this linear regime. As you know, with materials, some of them get harder. With strain, some of them are ductile and just start flowing after a certain stress. No further stress is needed. Some of them just break. Okay? So there's some place where elasticity will break down. We are working, generally speaking, well in this linear limit. However, though the relationship between strain and stress is linear, the relationship between stress and displacement, it isn't necessarily linear. Okay? So all the nonlinearities are purely geometric. Physically, everywhere in the material will be at small strain. Okay? But to describe the strain correctly in terms of the displacement, you need to hold on to everything. Okay? So just to be clear, we are not going to deal with this phenomenon or this phenomenon where it will never recover. Everything here is reversible. Okay? Yeah. Yeah. In you. Oh, over here? Yeah, I'm not going to put in material nonlinearities, but that's many materials are nonlinear actually. Many materials don't look like this. Many materials actually will start doing something smooth. But let's leave material nonlinearity out of it for now. I think it's the thing I wanted to say. Okay. Just that to correctly account for strain, even small strain, you have to account for large displacement. That's the only point I wanted to make. I want to quickly go over that stuff also, but while we're talking about Young's modulus, I wanted to show, anyone has any idea what the Young's modulus of anything is? Not bad. Give Newt Pascals. Okay. Not bad. You're off by only 1 order of magnitude, and it's such a huge number, it's okay. So here's some materials, okay? So these are things with holes in them, okay? These are things with lots of gaps in them. These are things with, this is water density and above. These are, you can see these things are, they have, they're forms basically, but the others are sort of some kind of bulk solid of some kind. And you can see that just in nature, you can get a huge variation of these things. Okay. You are right. So metals are up here. They're up at the 10 to the 11 range. Okay. And fancy engineered alloys are higher. Diamond is harder. Graphene in plane is very stiff. But, down to here are fairly normal materials. And that gives you already, I don't know, 3-4 orders of magnitude on the y-axis without doing anything unusual on the x-axis. And then if you go to polymers, these are very common materials also. This blue blob, thank you. Sorry, yeah? So this blue blob is also fairly common materials. Many things you handle in your daily life are around here. So you can get from here to there very easily. So do you know whether this is large or small? Compared to what? Okay, what's atmospheric pressure? Say again, 10 to the power 5, right? So atmospheric pressure is down here, right? Down here. This is atmospheric pressure. Okay? So you get some sense of how much strain you are under atmospheric pressure. These things are actually, you can go to the low end of elastomers, and it's actually not trivial amount of strain. If you suck out the atmosphere, they will swell a bit. As people who do this kind of experiment sometimes realize after their experiment has made a mess. But this is relatively, it's negligible strain. Okay? So, what's the pressure of a person standing on their feet, roughly? 10 to the power 4-ish pascals. Is that right? So you do, what are you taking? You're taking a 100 kilogram person and 10 newtons, okay? 10 meter per second square, so there's 1,000 newtons. And I'd say this is less than meter square. So I'd say probably the number's larger, but not a whole lot larger. But you can see that, these are perfectly good things to stand on. Okay? This is getting not so great to stand on. Okay, those are the materials you use when you want to absorb impact, for example. Okay, so just so you have a sense of where materials are, I want to come back now to where we were yesterday. So we talked about now going to 2 dimensions, which meant integrating over thicknesses. So we thought about taking a material like this and compressing it or stretching it in plane. Okay? And what you want to do is integrate the compressive stresses over the thickness of the material. And you find that this object, the integrated sigma yy, sorry, this is y direction. I'm not sure why I do this, but everything is y first, not x. Okay, sigma yy is just a material constant times epsilon yy. The material constant is Young's modulus times the thickness. Okay, so just a small warning here. Now I've changed stories on you a little bit. Okay, this thing is a 2-dimensional object. This I've integrated over a thickness, no? So it's force per line. Once we stop drawing objects with thickness, I'll in general use force per line. And I'm inconveniently using the same symbol as force per area. Okay? But understand that everything is integrated over thickness now. I won't write sigma superscript 2D for everything. I'm just going to write sigma. This is energy per area. Okay. All right. Then we made some hand waving to say that the bending energy, which is the other mode of deformation, that's to say you can either do this or you can do that. And we were trying to estimate what that would cost. So what I would ask you to imagine is some material that's doing this, and then we zoom in on some piece of that, and we look at that piece, okay? And let's say this from its undeformed state, the height is zeta of y. Is it zeta? Maybe zeta. I asked to zoom in on this piece and look at this piece, and then you should realize for this piece, it pays nothing for slope, it pays nothing for, I'll make this a little bit better soon, but this was the argument we made yesterday. We pay nothing for slope, we pay nothing for displacement, but we pay for doing this. And we pay equally for doing this and for doing this. Okay? So the first level of hand-waving argument is that that the energy density is proportional to the square of the second derivative, the curvature. Okay? So that's what we wrote over here. And then we did dimensional analysis to say, well, this B, what can it depend on? It can depend on these 2 numbers, and it can depend on the thickness. The only dimensionally correct thing is thickness cubed. Okay? And the thing I asked you to realize at that point is that these are dimensionally different. Okay? Right? This is 2 length dimensions more than this. But if, for example, you use the size of the sheet to compensate for those dimensions, then you can see already from this that bending goes, as thickness becomes smaller and smaller, bending becomes easier and easier. This becomes a really small number. We'll talk about that a little bit more. But first I wanted to say a bit more about where this comes from. Abhishek, for example, walking in here asked me the question that, look, all these strains, they were first derivatives, and the energies were first derivative squareds. Suddenly you've pulled second derivative on us. Where did that come from? Let me try and give you, I won't do the full-blown nastiness of this, and I will refer to your book, but let me tell you how the calculation goes. Let's imagine I'm looking at a piece like this. What you should see is that if I took block like this and I bent it so, then material lines on the top surface are getting extended. Material lines on the bottom surface are getting compressed. Okay? So you have, I don't know, a material line that used to be a certain length, now is this length, and that same material line over here is compressed. And this is, sorry, this is under tension. Okay? Somewhere in between, the material is neither compressed nor under tension. There's some neutral surface here. Both these pieces of material, this one at the bottom and that one at the top, used to be this length when this thing was straight. Okay? So here, if you ask, again, this is wholly inappropriate for this, the way I've written it, but let's say that's Y and let's say that's Z. Okay? The strain in this direction, it's EYY in this direction. Okay? It's 0 in here. It's negative here, positive there. Okay? And it's, if you like, we can do this in terrible, painful detail, but you get the idea. If I'm looking at some height Z, then the length, let's say I'm at some, let's say the radius of curvature here is this, and something like this. This is what the strain looks like, right? Yeah? It's the length of this arc minus the length it used to be divided by the length it used to be. So this is Z over R. Okay? I can do it better, but so these are the 3D strains, which are all gradients. But when I integrate the 3D strains over the volume, then I need the gradient of the gradient. And wait in a second. Sorry, let me, just for staying on this side, if you don't mind, I'm just going to erase this. The R goes all the way to the neutral line. Thank you so much, yeah. Not that it, yeah. R goes all the way to neutral line, yes. Okay? So the energy density should be regular old E times Z over R squared dz integrated from minus T over 2 to T over 2. Okay. So really what you get it, there's a gradient there, there's a gradient there, this is the difference of the gradient that's contributing to this. That's why you get it. Microscopically, that's why you get another gradient. Okay? So this is, as you can see, this is going to go as E T cubed times 1 over R squared. Okay? If you do this in full detail, can you see the detail that I've skipped? I've skipped the fact that there's other directions. We said this in detail, right? If you have forces in one direction, you have compression and expansion in other directions. I haven't put in those details. If you do the whole gory thing, let me write the answer in that far corner beyond the forbidden zone, because I'll just leave it there. It's useful to know. This is beyond forbidden zone, right? This is, the whole thing gives you this. Okay, but ET cubed. This number is close to 10. So if you call that order 1, that's order 1, but it's a number. Okay. So if you do this right, you get that. Okay. Plan for the day is now to move on to some instabilities. Okay. And we'll today do one-dimensional instabilities. Okay. We'll try and do buckling in one dimension, and we'll try and do wrinkling in one dimension. The old buckling problem, which actually predates a lot of this formalism, is due to Euler. That's a picture. The left side is from Euler, and the right side is from Lagrange. So what he's thinking about is the very practical problem of, suppose I put weight on an object, when does it decide not to compress, and when does it decide to bend instead? Okay, that's the thing they're thinking about. The calculations with Lagrange also consider more complicated ways of failing. You know, can you, instead of doing this, can you do this or that, or, you know, et cetera, et cetera. This problem also comes in various slightly different flavors, and you can imagine this. So this is why I was asking for a ruler. It's more satisfying to do it with something that you have to push on for a little before it goes. But if you push a little bit, the question is, do you get compression, or do you immediately start getting this? That's one question. Next question is, which we won't talk about in detail, is like many, many other problems you have dealt with in life, boundary conditions can come in various flavors. So I can do this problem in which I fix the displacements at both ends, but I don't apply any torques to the thing. And I can do this problem in which I clamp and push towards, and I can do mixtures of these, just like you've done various mixed boundary condition problems in, I don't know, electrostatics. Okay, so this is the problem we'll think about for the next while. So what I want to tell you, the result is, of course, pretty old, especially the first way that I'll tell you. Yeah, we're going backwards in time a little bit from yesterday. But I think I want to tell you this in some detail, because from the standard way of telling the story, there are some lessons missed, at least in my education, which I only learned again when I started working on all these problems. So I'll spend at least half an hour on Euler buckling. The quick version we can do in 5 minutes, but I'm going to be a little bit painful and slow. Okay? Because I think there's some nice things to be said about it. And some of those things will become clearer as why I'm putting you through this pain will become a little bit clearer when we see more complicated problems that are not one-dimensional. Okay? So just bear with me a little bit. Okay. So you got the problem that we are after. We're going to I'm going to stop drawing things with thickness now. I'm just going to draw lines, and I'm not going to draw this dimension anymore because we've integrated over that dimension and we just have two numbers now. Okay? So I'm going to start with a plate that's this length. Let's call it W. And I'm going to work on the flavor of the problem where, let's work on this problem rather than this problem. It's actually worth, I suggest trying it out in my notes. The other problems, they're not so much different. Okay? So what I'm going to do is start with something like that, and then I'm going to keep this end fixed, and I'm going to insist that this end moves in by some distance. Insist that moves in by some distance, capital delta. Okay? and ask, what would you like to do? Right? That's the question. So I'm going to do this in two ways. One way is to allow it all its possibilities. It can bend or compress or do anything it likes. But let's first get a feeling for the problem by treating them separately. We'll do two options. Option one, you only compress. Okay? All right? And option two, which we'll move to next, is, so this is pure stretching. Stretching is probably the wrong word. Pure compression. Pure stretching. And then the next one we'll do is pure bending. Okay? So let's work it out this way first, and then we'll try and allow it to have both possibilities, and we'll see how the picture changes. All right. So pure compression is straightforward. Here, again, as always, this is the y direction. This is the z direction. And let's say the direction coming out of the board is, this thing is infinitely long. Let's make it a really one-dimensional problem, okay? So you have something that comes out as far as you like. So no dependence on x. So epsilon yy is just delta over w. Okay? It's good. And that's done with that. So if you do this way, the energy density for stretching is delta over w squared half y. All right? And then I must, to get the whole thing, I must integrate along this, and that's per length in this other direction. Okay, so this is energy per area. All right? Now we do pure bending. Now what does pure bending mean? Pure bending means that you are only bending and you're not changing length at all. Okay? So there's material points inside the sheet don't change distance. Of course, you know in 3D all kinds of actual strains are going on. But in 2D, no strains. Okay? Just pure bending. That's what I mean. So, let's say the shape is, in pure bending, is zeta of y. And what this pure bending means is this thing is inextensible, or I don't know. Inextensible is the word used. I mean, here it's not going to be extension, it's going to be compression. But there is no technical word for uncrunchable. I don't know. But what you want here is the following. You want to say that when you integrate from 0 over its length, that's to say if I follow this contour, dy equals, that's what this means. Is okay? Everyone's happy? This is just just integrate the length element over this. Could you say again? I'm just saying the contour length along here is the same as this original length. That's what I was trying to get at. That's right. So I do this, and what that constraint here says is that the length along here is the same as this length. Right? So this is the W, and this is just the length element going along here. Everyone fine with this? Complain now or don't. You can complain later also. Yes. Sorry. Thank you. At least the first time I should write it out officially, right? Psi prime is there's only y dependencies here. Okay. Sorry, this is just, have I made trouble here? This is just dx squared plus dy squared. No, this is just dy squared plus dz squared. It's just the length element, okay? And so this is a constraint that I have to keep, all right? Let's say I'm looking for the place where it, let's say I'm not looking for this situation, okay? Let's say I'm looking for moderate slopes, then I can make this a little bit less hairy. I can say that, I'm going to do this. Okay. Then this thing turns into, the one gives me a W minus delta. This is whatever it is. So this turns into half psi prime squared 0 to W minus delta dy. I still have a minus delta equals 0. That's what the constraint looks like in small slope. Okay. What does the energy look like? The energy looks simple. The energy is just half B, and then we have second derivative squared. All right? Oh, thank you. All right. So this is why I asked you to please look over how you work with a string or how you work with Lagrangian densities. I'm not going to do the whole functional variation, okay? I'm just going to write the Euler-Lagrange equation down. But you remember how you do this? You have this functional integrated over dy with a constraint, okay? So you add the constraint with the Lagrange multiplier. I'm going to say, this is what I'm trying to minimize. I'm trying to minimize EB integrated over dy and a Lagrange multiplier, which we will suspiciously call sigma for now, times a constraint. Okay. And this is what I'm trying to get, this is what I'm trying to minimize. And this gives me the Euler-Lagrange equation, which looks like this. 1, 2, 3, 4. 1, 2. Okay? It's a little bit nastier than the things that David was knocking off you this morning, just because there are two more integrations by parts to do. Okay? Do you remember how you get from q dot squared to q double dot? Yeah? And how you get from just v to gradient of v. Every time you do one of these, a boundary term goes away and gives you another partial. So these two derivatives turn into 4 derivatives. Okay? This is worth doing once in your lifetime, and then maybe once again when you plan to teach a class like this. But whether you want to show your class or not is a matter of taste. Okay? So this is 0. Oh, sorry, I'm speaking as an experimentalist. The rest of you, please do it all the time. Okay? Do it for fun. Okay, so what's the solutions to something that looks like this? What's a solution to something that looks like this? Yeah, so I mean, if I got rid of these, you would have been happy, right? So it's just a bunch. You can get trigonometric solutions to this, right? Say again? Sorry, I missed some problem. Are we okay? Okay. So I'm going to write solutions that look like this, like a sine of qy. Say again? I'm missing something. So everybody's worried about something. Oh, I'm so sorry. Yes, I see why people are a little bit worried. I'm so sorry. Yeah, I knew there was some trouble here, and I couldn't figure out what the problem was. Okay, and the Q here is just root sigma over B. Okay. Yeah. And if you yes, now I use boundaries to get rid of them. So right. So if I'm looking for shapes that are pinned here and here, okay, I lose a whole lot of them, and in fact, I'll want this thing to be pi over w, right? So that's what sigma b. I want that whole thing to be in the lowest mode. I want it to be pi over w, right? And you can do all the higher modes you care about. So I actually get sigma equal to pi squared b over w squared. Okay. So this is the Euler-Lagrange equation you get from doing a variation on psi. Somebody please tell me what the symbol is called. Psi? Okay. Okay. 2 minutes. Okay, good. Psi. So this is what you get. And the interpretation of this is actually the stress. This is the force that you're pushing on with this in this direction. Okay. Now, what else did I want to show? What else did I? Yes. But you get one more equation, which is just the equation of constraint, right? I vary with respect to sigma. So I should go put this thing into the constraint. And what that gives me is, so from varying sigma, I get I should put this guy into there, or into there actually, into the, did I erase the constraint? No, into this. All right? And now I'll get a constraint on, the constraint will become a constraint on A. And I'm going to write that down. Okay, so 0 to W minus delta half A squared Q squared cos squared QY dy equals delta. Okay. So this is going to give you a 1 plus something, and so you integrate this out, and I have at the end of this, I have an A equals 2 over pi root delta W. Okay? And I hope I did that right. The root delta W is definitely right. The root delta W you can get very cheaply, right? You can do it. The root delta W you can just do by Pythagoras theorem. So instead of doing this, you can say this. That's the amplitude. This piece is W. This piece is W over 2. This piece is W minus delta over 2. And that will give you that. It'll tell you already that it goes as square root delta W. But if you integrate over the arc, you get the 2's and the pi's. So what this gives you is that EB is half B, and now we want two derivatives of this. Q squared A sine QY, quantity squared, which you will integrate over the whole length. Okay? Let's start putting in things for this. So this is a half, a B, a y squared over W squared, and an A, this quantity squared, and an A squared, which is a 2 over pi delta W. Okay? And after many calculations, I'm leaving out the sine squared QY part, but this, when I integrate over y, it's going to produce for me some constant. Right? It's going to produce for me a half or something. I get a B delta W cubed. Okay, so so the result is hidden here, and let me make it a little bit clearer. So in pure compression, what do you get? You get that when you push this thing, that the energy scales with delta squared. Okay? And in pure bending, the energy density scales with delta. Okay? So, what does all of this say for us? I'm going to erase yesterday's stuff. By the way, is this really forbidden? Is this useless to use? Or can I write here? Okay. So what I wanted to get for you is this. Huh? First is, you get a transition at delta equal to some critical value of delta in this way of doing things when EB equals ES. Okay. And that's to say B times delta C over W cubed equals Y times delta C squared over W squared, which says, I'm going to collect 1 delta, okay, delta C, and I'm actually going to keep a W here to keep this dimensionless, equals B over YW squared. Sorry, I need to step away to see if I've... Okay? Looks okay? So that's where this comparison predicts a transition from pure compression to bending. Okay? You might have seen this coming when you expressions. This is delta. And let's say this is the energy density. You saw that, you know, the pure compression is like Hooke's law, it's quadratic. E stretch, and the bending is linear. E stretch, and so this is the place where they cross. All right, so the idea is that you get the stretching solution till here, and then you get the bending solution. Okay? And the place that this happens is given by this. And the interesting thing about this is that this scales as approximately ET cubed, E times thickness, W squared, which is just T squared over W squared, maybe with some prefactors like 12 times 1 minus something else squared, okay? But the point is that this is purely geometric. It doesn't matter whether you make your ruler out of steel or plastic, it's going to buckle at the same displacement. Okay? E cancels over here. Right? And this thing is called, actually 1 over this thing is called the von Karman number. You'll see this here and there. This is called the von Karman number. So this is von Karman inverse, sorry. And you can see that this is a problem only for thin things. For bulk things, probably worse things happen with material nonlinearities before things break like this. Okay? So this is one piece of information we got out of this. We got another couple of pieces of information that are compatible with that go with this picture. If we drew the amplitude, the story is it's 0 till here. And then I start somewhere here and I get a square root delta W with a something or the other behind it. Okay. Yeah? Finally, we got a stress also. And the stress in the beginning was just Hooke's law. Stress is just y times this, right? So the stress went linearly negative for a while. But then the stress over there is a constant. So once you hit delta C, it takes no further force to make this keep going. Does this make sense? Yeah. Could you say again the sine square? Oh, what I should really do is I should really integrate this whole thing over dy, okay, to find the energy, not the energy density. it's going to give me something like a half over there. So really, what should I compare? I should compare EB, which is integral EB dy, and I should compare it with ES, which is integral ES dy. And this will just be multiplied by the width. That will be width times, I don't know, this is going to be 1 plus cosine 2 something, so it's going to give me a half somewhere there. So you're right, I may have got a half somewhere missing, but this is the general picture, okay? One thing I want to point out is that this looks like a very linear problem. It looks like the kind of problem that you've seen before, except more derivatives perhaps. But I want to show you one small thing that when we do the more painful, sorry, this was the less painful version. I'm going to do a more painful version just now. Is that it's not like a standard wave problem that you've seen before because of the constraint. You do any of these wave problems, there's nothing fixing the amplitude, right? Amplitude can be anything in such a solution, but the constraint, which is actually some nonlinear constraint, fixes the amplitude, and it ties the amplitude to, you know, some global displacement. Okay? So it's a little bit different from maybe a wave on a string. And that's because the constraint of inextensibility in the next thing we'll do, inextensibility will show up in a slightly more poisonous but apparent fashion, okay? Yeah. In general, it could be a Fourier series, right? So, that's something that I would ask you to try. As you can guess, it's not so much more difficult. Here are interesting things to try. Try mode 2. You can almost immediately guess this is more energy, right? I mean, there's more bending going on here, right? So it's going to be a higher mode. You can tell almost by inspection. So the question you might like to answer is, how much higher? But the more interesting question is there a barrier between this mode and this mode? And that's, I think, a harder question to answer, but it's a more practically relevant question. That's to say, if you start off like this, will you become like this later? Or you have to do something to it. You have to kick it over into the other state is an interesting thing to ask. No, you can get, you're right, you can get superpositions if you want. Absolutely. Yeah, the whole Fourier series is available to you. Yeah, please. For clamping, you said the derivative to be 0. For non-clamping, I haven't explained this in detail, and I won't. You set the curvature to be 0 at the ends. Second derivative is 0 at the ends. Yeah. This is pretty straightforward to show. But I want to show that the picture is actually a little bit more complicated than this. So can I forge ahead? Okay. I'm sorry, I'm doing this in painful detail, but it'll help in problems that are not as easy to solve. So what I'm going to do next, to just belabor this point, is now not do these two simple limits. After all, who told the material that it had to choose between option A and option B? Why can't you do a little bit of both? As you can see in that diagram, especially near the crossover, the cost of bending and stretching are comparable. So who told it to choose completely a bending solution as opposed to only a stretching solution? So now I'm going to leave it both options. I'm going to leave it the possibility of doing stretch plus bend, and please minimize yourself whatever you need to make this work. Okay, so this is half y EYY squared plus half b psi double prime squared. Okay, I'm going to now ask you to do this. And so let's get this, let's try to get this right. So let's take this shape and we allow it now any combination of displacement and strain. It could actually be compressing in some places. It might, it might not do this. It might actually give up on some of its length and it may bend a bit. So both options are available. So let's start off by writing what the displacement is. So the displacement is, of course, just a function of y. So it's some piece in plane, okay, plus some piece that's out of plane, both functions only of y. So this is the strain. That's step one, right? Is in this business. This is the displacement. So can you help me out with the strain over here? Can you tell me what I should get for epsilon yy? So diuj plus djui plus diuk plus djuk. So there's only derivatives with respect to y that are left. Thanks. So thank you, exactly. So the first bit is just the dyuy. So dy of u, right? This is from the diuj. So dyuy, and there's half, and there's two of them, plus there's a half dy of psi squared plus a half dy of u squared. Yeah? Does this make sense from what we talked about earlier? I'm going to go to the invisible area again. Yeah? Good. Now, I'm going to just keep the lowest order term in each thing, so I'm not going to deal with this thing. Okay? You can go ahead and go to town, please yourself, and use that also, but I'm just going to keep the first available term in each one. And you can see I absolutely have to keep this, right? This is all the out-of-plane things. And it came from that nonlinear piece in the strain. Stress is sigma yy is equal to y times EYY. Okay? Okay, writing Euler-Lagrange equations is not more difficult. It's the same thing. I want to take this thing, okay, except I have, except I have a more complicated object in here in terms of use. Okay? But that's fine. So I get two Euler-Lagrange equations. one respect to varying with the u, and one I get with variations with respect to psi. Okay? So the psi one gives me something that looks 1, 2, 3, 4. And the other one gives me psi y prime equal to 0. That's to say psi y equal to a constant. By the way, I'm sorry, I'm keeping these tensor indices. I don't need them. This is a 1D problem. There's only one thing, but just keeping them to remind us because we'll need them very soon. Okay? So these look familiar to you from the last problem, but I want to tell you they're not. And they're a little bit more dangerous. You see what's going on here? This is y times dy of u plus half dy psi squared. That's the thing that's constant. Okay? So these are, when you look at displacement, you realize that these are actually coupled and nonlinear. So they're a bit nasty. And they're not things that I know how to solve, but I'll show you what we can do at least perturbatively. Yeah. Sorry, this capital Y is the stretching modulus. Yes. Yes, that's right. Please. What I'm doing is I'm trying to keep the lowest order in each deformation. Okay? This is not 0, but it's higher order than this. And this is a nasty enough problem at this point. Okay? Full-blown Euler in 1D is already slightly painful. I just want to make some comments before we try to do some algebra and get some solutions out. And the comments are, by the way, these go by the name, these are an example of what are called the Foppel von Karman equations. They always look like this. They can look more complicated in different geometries, but they have this flavor. This thing is actually force balance out of plane. This thing's trying to bend, and this is the force that's trying to keep it straight. Okay? This is force balance in plane. Okay, so these are equivalent of, these are both force balances, and this is normal direction and in plane. Okay? So the way we're going to try and solve this is by perturbing a little bit about the planar state. So we go in thinking, let's imagine that we know from real life that there is a planar state somewhere and the planar state becomes unstable. We're going to go and try and perturb around this place. Okay? So we're going to start off by saying we know what the stress is in the planar case. And we know what the displacement is in the planar case. And then let's try and work for small amplitude. Let's say the out of plane thing has a small amplitude, and that's what we're going to try and do. Okay? And presumably the amplitude, that's not what that picture says, but presumably the amplitude is small when it first goes. Okay? So we'll try a series solution, and I will solution perturbing about planar state. So the first thing I'm going to write is u of y is just minus delta over w y Sorry, I'll try and keep these script and the other ones capital. Okay? Plus more. Okay? There's other stuff. This is the first term. Okay? This is what I get from the planar state. You agree? This is regular just contraction of this thing in line. And then I'm going to say zeta of y is some amplitude which depends on delta. Okay? And this is small for now. And I'm going to just try the first term in a Fourier expansion plus other stuff. Okay, plus other terms. And what I'm going to do is I'm going to put this back into the first von Karman. Put into 1. And I get B pi over W 4 powers linear in A minus sigma YY pi over W squared linear in A equals 0, which of course just gives sigma YY is B pi squared over W squared. Okay? But remember, sigma YY is y, no, I shouldn't say just, is this guy, which is y times first derivative of u, so that's minus delta over w plus half a squared pi squared w squared sine squared y over w. Okay? So that's y times minus delta over w plus pi squared a squared. I'm going to make this so 4w squared plus an oscillating term. This better be fixed by later terms in the series. I will optimistically not discuss convergence and blah and blah, and say this is going to be fixed by other terms in the series. Let me start labeling things a bit. Do I need to label them? Okay, so what you get from, yeah, let me call this guy 3, this equation. Where's 1 and 2? Yeah, 1 and 2 were those two. And let me call this 4. So if I look at, if I put 3 and 4 together, you maybe begin to see what I get. I can't erase the pictures. Okay. All right. I shouldn't have erased that. That's one of the worst boards to have erased, but doesn't matter. I get a squared equals 4 over pi squared w delta minus pi squared b over y times w. Okay? Or 4 over pi squared w times delta minus delta c, where delta c is this object. Okay? So, let me just write that out. Delta C is just, again, I'm going to non-dimensionalize by this. I'm going to get B over Y W squared. Okay? So it actually gives exactly the same threshold as earlier. But you see that it changes this picture quite a bit. It changes this picture by saying this is not first order. It actually does something like this. Okay? You don't jump into a new state. You grow from delta C. The convenient thing and the nice thing actually is if you look for very large, if you look at this is the Elastica solution. Oh, this is the pure bending. I didn't use that word. I should have used that word. Okay? So what we did by doing the rough job, I must say this is a coincidence in this problem. The first bit of the series expansion we did was meant to work for small amplitude. And I'm saying, please let's see what it looks like at large amplitude. It happens to actually match up with the Euler way of doing it. Okay? So we did this problem in two kind of different ways. This is sort of a near threshold of perturbation kind of expansion. This is the way you do most instabilities. You look at the flat state, you take all the stresses and the patterns you had in the flat state, like this, and you pretend that this amplitude is small, and then you ask what solutions exist. Okay? This was a fairly ad hoc way of doing it. Okay? It turns out that the thing that works near here and this way of doing it give exactly the same threshold. They change the character of the transition, but they match up at large values when you're very far from the transition. So this near threshold picture happens to match up with the far from threshold picture, and that's an accident in Euler buckling. And I want to tell you that it's an accident because it doesn't always do it, and we will soon hit problems in which in which the answers look different. Okay? I didn't tell you a word which is very commonly seen in this literature. This pure bending thing, which Euler considered, is called an elastica. An elastica is something that can bend with no energy at all, won't stretch ever. So this thing is called the elastica. The strong thing that is retained is that the threshold again depends on just the von Karman number. It's the same threshold, and it's completely independent of material. There's only one axis that drives all the action here, and that is this delta divided by delta C. And this is the control parameter of this whole problem. I want to say that that thing, of course, has more information in it. And before we go on to other problems that have more interesting looking answers, I wanted to just show you what this thing looks like. So the x-axis of all these figures is delta, delta. Okay. I just wanted to show you what this number looks like. So this is what's driving all the action. Change that number and you change things. So this is delta divided by B over Y W squared. Okay. I'm just going to write this as delta over W. And I'm going to add another y squared there. Did I erase it? Sorry, have I acquired too many? Is that what you're saying? Thank you. Yes, thank you. Perfect. Thanks. So, I want to say that this delta over W is the actual fractional strain, imagining everything is inline. So this is just the compression, imagining everything compressed uniformly. This is if I use what I've got for stress, B over W is stress, right? This is delta over W times Y over sigma. Okay, so this is the actual compression I needed to apply. These are two different kinds of strain, and they happen to show up in this form. This one is something I do externally, and this is the forces I need to apply externally. Okay? So if I were calculating strain just from force, this is what I would do. If I was calculating strain from geometry, this is what I would do, and they cancel. They both show up in this problem in this way. I want to show you later on that things don't look as neat in other problems. So I won't get to do 1D wrinkling, but I want to at least start telling you where we are going. So if I take, we talked a little bit about higher modes. No, we do this, or we do that, or we do this. You realize that these are higher modes. But in some problems, you start seeing wavelengths automatically. Let's describe three problems. One is this, okay? You pinch your flesh between two places, you apply a displacement, and you start seeing wrinkling on your forearm. You can see that it doesn't make one big bulge. It selects a wavelength in between. The wavelength doesn't depend on the size of the region you pick. I don't know, go 3 centimeters apart and 2 centimeters apart. It's an internal wavelength. Okay? We have to figure out where this wavelength comes from. Here, the wavelength is the system size. As big as the system is the lowest mode you can find. That's one problem. Another problem that you can see, it's a little bit artificial in the curtains, but if you put clothes under tension, you start seeing internal wavelengths develop. If you put a material under tension like this. The third thing you'd have seen, which is probably the cleanest example, is if you've looked at the protein film on top of the milk on your tea or coffee, you press it a little bit or blow on it a little bit, you'll start seeing ripples. These are not ripples on your tea. These are ripples on the skin of the milk, right? And you can see it on milk also. So here's an example of wrinkles in 2 dimensions. This is sort of so these are one-dimensional wrinkles. This is a nice version of what I tried to do with my shirt. Okay. Curtains are a little bit fake example because there's already a wavelength selected at the top. You'll see with long curtains that they tend to choose their own wavelength. If they're not heavily crimped, as they go down, they choose another wavelength. I showed you the elephant trunk in the very first set of slides. That has a chosen wavelength. So this is just 2 things clamped and pulled. Okay. This one is maybe hard to think of. I want to show you another one that looks like this. So what's going on here is more like Euler buckling than pulling my t-shirt. What's happening here is I have a thin film. It's floating on water. So this is exactly like your tea or milk. And from both sides, I push. So I come with barriers from both sides and I push. It selects a wavelength. Okay, sorry, this is a razor blade. This whole thing is order centimeter, and the whole experiment is order 3 centimeters. Okay, and it selects a wavelength in between. Okay, so the question is, what's going on? Why does it go to higher order modes? What do we need to add to this problem to start seeing these patterns? And let me ask you, what's the difference in physics between, what's the different ingredient here between this and this problem? Scale is one thing. This is spontaneous symmetry breaking in the sense it goes from here, it chooses between these two states. This also will do that for you. But what's the different physical ingredient? There's a sheet. It has the opportunity to stretch. It has an opportunity to bend. These are 2 energy costs. There must be some new ingredient. So the new ingredient, let me tell you, is that your skin, which is a hard material, hard but thin material, is sitting on top of your flesh. When you distort your skin, you distort the soft substrate also of the flesh. When you distort this, so what's going on here is, if I can draw here, is water, sheet, and compress the sheet. Okay, when you compress the sheet, instead of doing this, what it does is this. So what is it doing to the water? Say some more words about water other than surface tension. Okay, so what you're doing is, so surface tension is a relevant thing to think about in this context. It so happens that surface tension is not a big player in this pattern, just because what is the price for surface tension? It's for exposing more area. This sheet hardly extends or compresses. It stays the same area. So surface tension is a big force in this problem, but it's not, changing shape doesn't affect the surface tension cost. But hold on to the surface tension thought, whoever said it, for another day, and it'll start playing. But really what you're doing is you're paying a gravitational cost. You're paying energy for, you took this water and you put that water here. That costs energy. Okay? So what we're going to do is put stretching, bending, and some cost for a substrate to be deformed. The substrate could be a fluid, as in this case. Easiest case to think about is fluid. We'll work with fluid first. Then we'll think about a substrate being a soft solid underneath. And the third thing will be a substrate that's under tension. A substrate that doesn't want to deform because it's under tension. So these are the 3 things we'll talk about. And we have all the machinery. I promise I will not solve again for you 4th order nonlinear differential equation. We've learned what we need to learn. I think we've learned what we need to learn from that 1D example to work through this 1D example without algebra. Okay? And then we'll do this probably this will take us 10-15 minutes, having gone through this painful stuff. We know what to do. This will take us 10 or 15 minutes, and then we'll talk about 2-dimensional problems, which this set of information will not carry us through. Okay, see you.